Now I will talk about special relativity. There are three phenomena that occurs when someone is traveling at very high speed, close to the speed of light. The first phenomenon is the increase in mass, and the second phenomenon is length contraction, and the third phenomenon is time dilation. I will start with the increase in mass. Okay. Suppose the twin brother who goes on a journey in space weighs 89 kilograms. So his weight, as I have already said, is 98 kilograms, and in order to get his mass, there is a simple equation that says that the weight equals to the mass times g. G is the gravity on Earth, that is 9.8 meters per second squared. Now I will explain what is the meaning of the gravity, that is 9.8 meters per second square. That means that if you drop an object from the roof of high-rise building, then in the first second, the velocity of the object will be 9.8 meters per second, and in the second its velocity will be 19.6 meters per second. In the third second, its velocity will be 29.4 meters per second. So in every second, the velocity of the object will increase by 9.8 meters per second. So in the 10th second, the velocity of the object will be 98 meters per second. Okay, so the weight equals to mass times g, and if the weight is 98 kilograms, this equals to mass times g, that is 9.8 meters per second square, and we divide 98 by 9.8, so the mass is equals to 10 kilograms. The mass of the twin brother on Earth equals to 10 kilograms. So when you will move in the spaceship at a speed of 80% of the speed of light, that is 240,000 kilometers per second, according to the mass increase equation of special relativity, his mass in space will be 16.33 kilograms. But he will not feel it if his twin brother has a mass detector. The detector will measure 16.33 kilograms. That means that his mass has increased by 63.3%. So now I will explain the equation of the increase on mass when someone is traveling at a very high speed. Yes, m equals to m naught divided by the root of 1 minus v squared divided by c squared. M is the mass of the object when the object or someone is traveling at a very high speed. Yes, in our example, m is the mass of the twin brother that travels in the spaceship at the speed of 240,000 kilometers per second. And m naught is the rest mass, that is to say, is the mass of the object on Earth when it is not moving at all. So, as we have already calculated, m naught is equals to 10 kilograms. Yes, and we divided it by the root of 1 minus v squared divided by c squared, and v is the velocity of the twin brother that travels in the spaceship, divided by the speed of light squared. So we see that m is equals to 10 kilograms, that is m naught, divided by the root of 1 minus the velocity of the twin brother, that is 240,000 kilometers per second, divided by the speed of light squared, and the final result is 60.33 kilograms. So the mass of the twin brother is actually increased from 10 kilograms to 16.33 kilograms. So it's actually increased by 63.3%. Okay. Now I will talk about the second phenomenon that occurs when someone is traveling in space at very high speed. The second phenomenon is length contraction or shortening of distance, shortening the distance. When you measure a distance between two objects that are not in motion relative to each other, let's assume that you measured a certain distance, so the distance between them will shrink when one of them moves at a speed of a very high speed, close to the speed of light relative to each other. So when you measure the distance between two objects, you get result, and when you measure the distance between that two objects, when one of the objects is moving at very high speed towards the other object, then the distance that you have measured when the two objects were not moving relative to each other, that distance will shrink. The distance between the two objects will be shorter when one of the objects is moving relative to the other object. So in our example, the distance between between Earth and the star Epsilon was 10 light years, and when the twin brother is moving in the spacecraft in very high speed, that distance is actually shortened to 6 light years only. As mentioned, the distance from Earth to the star Epsilon is 10 light years. When you measure it from Earth, from Earth, the distance is 10 light years, but when you measure the distance from the spacecraft that moves in the space at a speed of 240,000 kilometers per second, then the distance will be shrinked to 6 light years only from the point of view of the twin brother flying in the spaceship. Okay, so I will explain the equation. L equals to L naught times root of 1 minus v squared divided by c squared. So L is the distance between two objects, the distance between two objects when they are not moving relative to each other. I made a mistake. L is the distance between the two objects when they are when one of them is moving relative to the other, and N naught is the distance between the two objects when they are not moving relative to each other. And when we multiply L naught by the root of 1 minus v squared divided by c squared, we get the L naught, the distance between the two objects when one of them is moving relative to the other in very high speed. So in our example, as I've already said, the distance between Earth and the star Epsilon is 10 light years. But when the twin brother is moving towards the star Epsilon in the speed of 240,000 kilometers per second, then the distance between him and the star Epsilon will shrink to 6 light years only. Okay? But in addition to that, the height of the man in the spaceship also shrinks. And if on Earth his height is 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spacecraft shrinks to only 1.08 meters. So I will explain the equation. L is the height of the twin in the spaceship when it is moving at very high speed, or in general, L is the height of an object that is moving in very high speed, equals to L naught. L naught is the height of the twin on Earth. On Earth, the height of the twin, or something that you measure in Earth. In our example, the height of the twin is 1.8 meters, but in general, L naught is the height of the object when you measure it on Earth. And when you multiply it by the root of 1 minus v squared divided by c squared, we get the L, that is the height of the object when it is moving in the space at very high speed. Okay, in our example, the height of the twin brother is 1.8 meters, that is N naught, and we multiply it by the root of 1 minus v squared. V is the twin's velocity in the spacecraft. It is 240,000 kilometers per second, and we divided it by the speed of light squared, and we get the result of 1.08 meters. So we can see that the height of the twin brother shrinks by 72 centimeters when he is traveling in the spaceship at the speed of 240,000 kilometers per meter. Okay, and if the twin brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay? Now I will talk about the third phenomenon that occurs where someone or something is traveling at very high speed in the space. The third phenomenon is time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took 25 years for the twin brother to return from a journey in space, in the spaceship the total time that it passed is 15 years only. So, first of all, I will explain the equation of time dilation. T is the time that is passed in the spaceship that is traveling at very high speed, equals to T naught. T naught is the time that is passed on Earth during all the journey, and we multiply it by the root of 1 minus v squared divided by c squared. V is the velocity of the spacecraft that is traveling in the space. Okay, and in our example, the total time that is passed on Earth during all the journey of the twin brother towards the star Epsilon and back from star Epsilon to Earth is 25 years. And actually we multiply it by the root of 1 minus the velocity of the spaceship squared divided by the speed of light squared. So 1 minus 0.8 squared is 0.36, and the root of 0.36 is 0.6, and when we multiply it by the 25 we will get 15 years. So the total time that is passed in the spacecraft that is moving in the speed of 240,000 kilometers per second, the total time that is passed during all the journey is 15 years only. So we see that actually the twin brother that is on the spacecraft actually will be 10 years younger than his twin brother that stayed on Earth. While from the point of view of the twin brother who embarked on a space journey towards the Epsilon star, he is at rest, and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of distance according to special relativity, and the total distance between the Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at the speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of distance between the spaceship and the star Epsilon as mentioned. So from the point of view of the twin brother that is on the spaceship, he is at rest, and the star Epsilon is moving towards him at a speed of 240,000 kilometers per second. In this situation, there will be a contraction of distance. The phenomenon is contraction of distance between the twin that is in the spaceship and the star Epsilon. The distance will be contracted from 10 light years to 6 light years only, and the total trip back and forth will be of course 12 light years, and so the total way is 12 light years, and when we divide it by the speed of 80% of the speed of light, we get 15 years, and we get the same result as we get when we analyze the it from the point of view of the brother that stays on Earth. From his point of view, there will be a time dilation, and that is the reason that the total time that is passed on the spacecraft is only 15 years. But from the point of view of the brother that is on the spaceship, because of contraction of distance between him and the star Epsilon, the total time will be for all the journey will be also 15 years. Okay, thank you very much.